For our third example, we're going to take a look at what happens if a rational function has two vertical asymptotes. And the reason this would happen is when I go to try to simplify or reduce this, the bottom will factor, but it won't cancel with anything in the numerator. So the numerator is x minus 1. It's always a good idea to put it in a parentheses. And keep in mind that parentheses is always there, even if it doesn't show up at the beginning. It's a good idea, especially when you see us graph points, we'll want those parentheses. So down here, we're going to be factoring 3 and trying to get negative 2. So 1 times 3 is the only multiplication fact in that problem. So we'll go ahead and put those here, and then we'll have x, and then we'll have the 3 be negative to make sure that we have a negative 2 and not a positive 2, and the 1 will be positive. So again, 1 minus 3 is negative 2. That being said, these two terms, they do not cancel. Even though they look similar, they're not the same. They won't cancel, like make a negative or something. So because nothing canceled, the whole does not exist. It doesn't have a whole because nothing reduced, nothing canceled, nothing went away. The vertical asymptotes will come from setting each of those factors on the denominator equal to 0. So our first one, if I subtract 1, would be x equals negative 1 is our first vertical asymptote, and x minus 3 equals 0. If I solve that for 0, I would get x equals positive 3. So there will be 2 on the graph. The horizontal asymptote comes from looking at the denominator's degree and the numerator's degree. Remember, if they're the same, you can just divide, but in this case, the denominator is larger. And when the denominator has a larger degree, the horizontal asymptote is always just y equals 0. If the numerator's degree is larger, we have a slant. Remember, you can't have both at the same time. So that will be our next example. In this case, it does not exist. Okay, so keep in mind, denominator is bigger, 0. And the reason is the bottom, if the bottom is bigger, it cannot divide into the top. It goes in there 0 times. Okay, so now we'll talk about the x-intercept and the y-intercept. So the x-intercept is to simply set the problem equal to 0. And so 0 is equal to the original problem, x minus 1 over x squared minus 2x minus 3. Now, luckily, this entire denominator will cancel. If I multiply by it here and here, it will cancel, leaving me with 0 times that, which would be 0 is equal to x minus 1. And if I solve that, I get 1 equals x. But of course, that looks like an asymptote, so we must write it as a point. That point is 1, 0. It'll later go in this chart. So the y-intercept is when you find f of 0, or plug 0 in. So that would be 0 minus 1 over 0 squared minus 2 times 0, and then minus 3. And so that'll come out to negative 1/3, negative 1 over negative 3, which is positive 1/3. So our y-intercept is we plugged in 0 and we got out 1/3. So let's go graph everything that we see and then see what we need to put in our chart. Before we do that, please remember that the domain is always just going to be able to be found by looking at the vertical asymptotes in whole. That's really important on a test. You don't want to have to graph the whole problem to do this. These two domain restrictions right here, these two things here will be in my domain as restrictions. Earlier, you would have set these two things not equal to 0, and you would have written them with a not equal 0. We're just going to put that into the domain. So the domain is x is all the real numbers in the world, comma means except my domain restrictions, which we'll place in order, and they would be negative 1 and 3. So the domain restrictions from your previous problems where you added, multiplied, divided, subtracted, they just go in the domain now. Okay, so now let's graph. So we have an x-intercept at negative 1, so I'll put that right here. And, we have a vertical asymptote at negative 1. And we have another vertical asymptote at 3, and our horizontal asymptote is at 0. So we'll label those just to make sure that everything's clear. So this is y equals 0. This is x equals negative 1, and this is x equals 3. And then we did get an x-intercept and a y-intercept. The x-intercept was at 1, 0. And you may say, oh my goodness, it's right on an asymptote. Remember, if you go back and look at the notes, it's okay to cross a horizontal, but you could never have one on a vertical. That would be not okay. Perfectly fine on a horizontal, as long as it goes to that value at very large and small, very small and large numbers. As long as it's trending towards there, it's okay. So you can cut through a horizontal, but not through a vertical. And so 1, 0 is our x-intercept. Our y-intercept is 0, 1/3. So right about 0.3. So now we don't have anything else. So we're going to come down here and put our vertical asymptotes in the chart with D and E as their value because they have no existing value. We're going to take a look at the x-axis and record values that are 3 smaller, just like we did for the other one. So -4, -3, -2, and then 3 in between. Luckily, we have them right there, right? So we have 0, 1, and 2. And then 3 a bit above, so 4, 5, and 6. We do get for free, right? We are going to get the x-intercept of 1, 0 and the y-intercept of 0, 1/3. Okay, and then we'll get started. So one of the things that's very valuable, and again, you can reach for a calculator, but my advice is calculators are something that you need to understand go away at times. You don't have them on portions of the SAT, AP tests, or in college. So knowing this skill I'm about to show you is useful in that respect. So to put -4 into the original problem is a bit of a challenge, especially on the bottom. But to put -4 in here, you would just get -5. And to put -4 in the denominators, right, we would just get -4 plus 1 is -3. And -4 minus 3 is -7. So that reduces very easily to -5 21st, but you would just approximate to be a fourth, -1/4. So the reason we're going to do that by hand, and I advise you can use a calculator to check yourself, but you really should recognize what this is going to be like to do by hand, so that you don't you don't think you have to put this into this crazy quadratic. If you can factor it, man, that makes your life easier. So -3 goes into here and gives you -2. -3 goes into here. Actually, that would give you, my apologies, that would give you -4. On the bottom is where that -2 is. So -3 plus 1 is -2, and -3 minus 3 is -6. So that would give us -4 over 12, which would be -1/3. Right, -4 divided by 12 is -1/3. If I put -2 in the top, I would get -3, right? -2 right here. -2 here would give me -1. And -2 here would give me -5. And so that would give me -3 over +5, or -3/5. When I come over here to the 2, it would be 1 divided by 2, and here would give you 3. 2 and here would give you -1, so that'll be -1/3. Put a 4 in here, you would get 3. Put a 4 in here, you would get 5. Put a 4 in here, you would get 1, so that'll be +3/5. So I'm going above that asymptote now. Put 5 in the top, you would get 4. Put 5 in the bottom, and you would get 6. Put 5 in here, 5 minus 3 is 2. You get 4 over 12, which is 1/3, positive this time. Put 6 in here, and you get 5. Put 6 in here, and you would get 7. Put 6 in here, and you would get 3, so you get 5/21. Now, some students will say, Mr. King, why did you do all that? You're possibly not going to have a calculator, especially in AP Calculus, to try that. That's a skill that will be valuable even in that class. So now let's record all those values that we have, and I want to tell you an important thing that I always tell my students. Do the outside, see how there's like an inside of the graph? Do the left and right side first. So at -4, I'm going to graph approximately -1/4, but -5/21. At -3, I'm going to graph 1/3, a little lower. And then at -2, I'm going to graph 3/5, which would be a little lower than that. And those might be a little off, so maybe we just bring them up a little, but they're close enough. It's just a sketch, so don't be so worried about absolute precision. And then on the next one, over here, I'm going to skip the middle. I'll explain why in a minute. At 4, you have 3/5. and then at 5 you have a third, and then 6 would be even lower. So we know that the left side is doing this, and the right side is doing this. Now, why is that important? Because your asymptotes are going to diverge. So inside here, right, if I graph my last remaining point on the inside at 2, negative a third, you can see that divergence, right? This is going down, so this has to go up. This is going up, so that has to go down. And the middle of the graph comes out looking like a cube. Now, the only other thing it can do is come out looking like a quadratic, and the way that would happen is if I have two vertical asymptotes, and both of my graphs on the right and left side went up, then the graph in the middle would have to be divergent down and down. It would look like a quadratic. So the middle graph can ever only look like a cube or a quadratic. So now we can determine the range. The range of this graph is all real numbers. And you may say, well, what about the horizontal asymptote? But didn't we cross it? And in fact, if you look at the middle, right, if I think about the middle here, beep the whole way. So you can also, if you wanted to, you could also write that in interval notation. That's perfectly fine. It's about the same difficulty to do both. You just can't write big R like you did maybe in middle school or algebra 1 potentially. So the end behavior as x goes to negative infinity, you can see that it's going to the asymptote of 0. So f of x goes to 0. And on the other side at infinity, it's also going to 0. And that is the other part of the problem, that if you have a horizontal asymptote, you do not need to see the graph, right? We don't need to make all this graph with all this chart to know this. It is always going to be, right? It is always just going to be the horizontal asymptote is going to be the end behavior. If you don't have a horizontal asymptote, that's when you have to look at the graph or use something called test points.